Problems 42 through 48 in Chapter 12 all involve working with gases in some way or another. So in question number 42, you're asked, what's the molar mass of a gas that takes 3 times longer to effuse than helium? Really what 42 is a problem involving Graham's law. So what Graham's law says is as follows. So it says that the ratio of the rates of either diffusion or effusion, it should be just rate, is equal to the square root of the ratio of their molar masses. Now the key thing to remember is that that ratio gets flipped on the right side of the equation. So that A is no longer on the top, it's on the bottom. Key to solving these problems is keeping whichever gas is A and whichever gas is B consistent. So at number 42, I'm going to call the unknown gas, gas B, and I'll call helium gas A. So we're saying that this gas takes 3 times longer to effuse than helium. So another way we could say this is that helium effuses at a rate that is 3 times faster than our gas. So when this happens, the left side of our equation, right, this side of the ratio of the two rates, just becomes number 3. Again, we're going to call helium our gas A, we're going to call our unknown gas B. That means on the right side, we'll put the molar mass of helium in the denominator. The molar mass of helium is 4.003 grams per mole. From here, it's just a matter of solving for our unknown. And if you do that, you end up with 36.03 grams per mole. All right, in the second problem in this chapter, number 45, you need to use Dalton's law of partial pressures. Basically, all Dalton's law of partial pressure says is that the total pressure of gas in a container is equal to the sum of all of the partial pressures, the individual pressures of each gas in that container. So number 45, you're given the total pressure of all of the gases, which is 1 atmosphere, and you're told that there's 0.79 atmospheres of nitrogen and 0.20 atmospheres of oxygen, and all these other non-water vapor gases make up a total of 0.0044 atmospheres, and you're asked to solve for the partial pressure of water. So all you need to do is set up your equation so that the total pressure is on one side, so in this case our total pressure is 1 atmosphere, and the sum of all the partial pressures is on the other. So we've got our N2, we've got our O2, we've got our everything else, and we've got our unknown, our partial pressure of water. From here, it's just a matter of subtracting everything but pH2O from both sides of the equation, and when that happens, you get your final answer that the partial pressure of water vapor is 0.0056 atmospheres. Number 48 is just a unit conversion problem. So you're given a total pressure of 84 kilopascals, and you're asked to convert that to atmospheres and to torricellis. Okay, the key thing you need to remember here is that 1 atmosphere, so 1 atmosphere equals 101.325 kilopascals, which also equals 760 torricellis. From there, it's just a matter of arranging your conversion factors. So in the first one, we want to cancel out kilopascals, so we want that in the denominator of our fraction. We want atmospheres, so we want that in our numerator. We're going to divide by 101.325. That'll give us a pressure of 0.83 atmospheres. In the second one, right, we want to cancel out kilopascals, so again, we get kilopascals in the denominator, and we want torricellis. We know that 101.325 kilopascals is the same thing as 760 torricellis, so it's going to be times 760 divided by 101.325. That'll give us our pressure of 630 torricellis.